Hi friends, today we are going to see that after sampling, okay, what happens to a signal, and then after upsampling and downsampling, what further effect does it put on the frequency characteristics of a signal. Now let us start first to understand what is a sampling. So sampling is a process which gives you a discrete signal, okay. So I have a continuous time signal, let's say x of t, and it produces, and I do the sampling on this signal and it produces x of n, okay. Let's say the signal is periodic with a frequency f hertz, okay, and when I sample again I get, let's say, a periodic sequence with small f, and I don't put any word to it. In the radian domain, the frequency is denoted as capital omega, let's say, which I write it as 2 pi capital F, okay, and in the radian domain this I write as small omega, which is 2 pi times of small f. But what is the small f? The small f is given as capital F divided by Fs, which is nothing but the sampling frequency. So I can write omega as 2 pi times of capital F divided by Fs, which is the sampling frequency. This small f is known as normalized frequency. Okay. Now from all background we know that this omega is having a unit of radians per second, whereas this omega is having a unit of radians per samples, okay, because this is in per second domain and this is samples per second, that second will get cancelled and you will get radians per samples, okay. Now what is the basic difference between this omega and this omega? We need to clearly understand. This omega do not have any bound or is not periodic, okay. If I draw, we normally draw this using S plane, wherein we have sigma over here and we have j omega like this, and that j omega goes all over from plus infinity to minus infinity. That means every signal will have, every periodic signal or every unique frequency will have a unique pattern data or unique pattern signal available for it. Like say 1 hertz, it's a unique signal. 10 hertz, it will also be a unit signal. 100 hertz, it will be a unique signal. That is not the case when we say a discrete signal or a discrete frequency. This is, I called it as analog frequency, small omega, I will call it as discrete frequency. Discrete frequency is periodic. The very first basic difference is discrete frequency is periodic, whereas analog frequency is aperiodic. If it is periodic, that means after certain values of frequency, the frequency is going to get repeated, okay. So after, let's say, some factor value, I am going to get the same values again and again. So the period of this is 0 to 2 pi, or we say from minus pi to pi. Just this is a recalculating concept or going back in the history kind of a concept, okay. So what has happened? When I was in the analog domain, I was having a unique frequency which is in radian domain called as capital omega and whose limits are from minus infinity to plus infinity. Now I sampled it with a sampling frequency of Fs and I got a discrete data. Now the frequency is now converted to a discrete frequency which is 2 pi of f, which is small of omega, which is periodic with a period of 0 to 2 pi and from minus pi to plus pi. Okay, this small f is called as the normalized frequency, and the unit for omega is radians per samples. Now, what basic difference does it make when I upsample the signal or downsample the signal? When we, let's say, upsample the signal, so let's take an example of upsampler. I have upsampled the signal by a factor of I, then this is the input sampling rate, which is fx, this is the output sampling rate, which is fy, and fy will always be greater than that means it will be I times of fx. That is a relation, correct? Now I wanted to find, because both are discrete signals, correct? So I can write omega of x at the input side, which is 2 pi times of f divided by fx, okay, and I will write omega y, which is equal to 2 pi times of f divided by fy, because fx is the sampling rate at the input side and fy is the sampling rate at the output side, okay. But we know that fy is related to fx. So if I put that value, what I am going to get is omega y to be equal to 2 pi f by I times of fx, okay. Now combining, see, I write like this, 1 by I, okay, and combine everything else, 2 pi f by fx. 2 pi f by fx is omega x. So what conclusion or what relation we can develop? The relation we can develop is omega y, that is output frequency, will be input frequency divided by I. What I did? I increased the sampling rate. What has happened to discrete frequency, or what has happened to the discrete frequency spectrum? Something very weird. Let us see what has exactly happened. So this is a very important relation that we have to look into, that is omega y is equal to omega x by I. How does it affects, and what are its effects? Let's say I have a signal which say x of omega, which is of some arbitrary shape. I choose it like this, going from minus pi to pi, okay. Now because it is periodic, what is going to happen? At 2 pi and at minus 2 pi, this signal is going to get repeated. Isn't it? So whatever the value is at 0, the same value will repeat at 2 pi, and it will same repeat at minus 2 pi, and so on and so forth. It is going to get repeat itself because it is periodic. So the spectrum I have drawn, which is obtained by doing DTFT, and due to sampling, there is periodicity of 2 pi. Now what I did? I downsampled. So let's say this was my omega x, okay. I concentrate now only on this signal, because rest of them are the just repetition of them. So let us concentrate only on this signal, what is happening from minus pi to plus pi. And now I draw omega y signal, that means a new sampling rate. What is omega y equals to? Omega y equals to omega x upon I. From the previous example, I say that let's say I equals to 2. That means I am interpolating, increasing upsampling by a factor of 2. So what I will get? I will get a new signal. I'll draw the samples like this: 0, let's say minus pi, plus pi, 2 pi, minus 2 pi, similar to that of the previous case. And this is my x of omega y, okay. Comparing omega y with respect to this one, when omega x is 0, okay, so when I am at omega is equal to 0, okay, at this point, fine, I put omega x is equal to 0, omega y is also 0, so there is not a problem. But now when I put omega is equal to pi, here I am going to get omega y as pi by I, which is pi by 2. So let us say this is the value pi by 2 and this is minus pi by 2. So what has happened? I had at 0 whatever it was. Now whatever value was coming at pi previously is appearing at pi by 2 itself. So what has happened? It has actually given me a compression. Okay, fine. What will happen at 2 pi? 2 pi factor if I put over here, it will be 2 pi by pi, okay, be 2 pi by 2, which is at pi. So now this factor will come back over here and it will go like this, correct? So whatever was happening at 2 pi previously, that has happened at pi. So what has happened? By increasing the sampling rate, the frequency domain characteristics of the signal is compressed. So at the output, okay, at the output, this is the graphical representation of the frequency response. At the output over here, what you got? A compressed frequency characteristics, and at the input it was a normal one. But at the output, by increase the sampling rate, this got compressed, and compressed by a rate of what? I. Agreed? And if you see from minus pi to pi, that much of window has been opened for me to observe what is happening. Now again I have omega over here and I see from minus pi to pi, what I observe? I observe from minus pi to pi, let us say, if I consider this signal, what I observe is there is one signal and there is half from this side, half from this side. That means there are again two signals available. That means there are, if I consider it to 0 to 2 pi, there are two set of signals. Okay, that means what happened? An image has created of the original sample. Okay, so by inserting more samples, you have compressed the frequency characteristics is compressed, and more images are created in the given spectra. Okay, so by what factor it will increase? Compress. It will compress by a factor of I. If I increase it by 3, okay, whatever value was coming at minus pi and pi will now come at minus pi by 3 to plus pi by 3, and whatever value was occurring at 2 pi and minus 2 pi, now it will occur at minus 2 pi by 3 to plus 2 pi by 3. Okay, so this will again further compress and there will be 3 copies of the signal. So in that case you will get, if I draw for I is equal to 3 case, you will get omega over here, x of omega, it will be, okay, now the signal will have from minus pi by 3 to plus pi by 3, then it will have one more set over here and one more set over here like this. Okay, so this will happen if you consider this will be from minus pi to plus pi. So there will be 3 copies. Okay, now as we have seen the case of upsampler, that we are going to get images, and I'm not interested into, because these images will give me the same information as what this will give me. Okay, we know that this is the spectral characteristics of the signal. Now it is just being compressed, but the spectral characteristics is as it is. So what I'll do, I'll just pass this characteristic, this much part, this much part through, okay, this much part I will pass through a filter. What will happen? I will only see this much of the signal characteristics, right? Rest everyone will be neglected. So I am hiding them all, and I am just opening a window for this guy. So what I am doing? I am interpolating, and then I know that due to interpolation there will be compression and images, and I don't want to see from minus pi to pi now. I have to just take the copy of one copy out of many images, and that copy I know lies between pi by I to pi by I, isn't it? It was first lying between minus pi by 2 to plus pi by 2. Now it is lying from minus pi by 3 to plus pi by 3. Here the I factor is equal to 3. Here the I factor is equal to 2. Correct. So I know that I have to just find where is minus pi by I to plus pi by I. If I will filter out this much of area, then I will get the original copy of the signal. Rest everything will be neglected. So what I am doing? I am taking interpolation, I am doing upsampling and appending a filter to that process. Why appending a filter? So that I will neglect the copies. So we have come across a very good observation that if I upsample a signal, time domain I don't have any problem. What happened in time domain? I have just inserted zeros. But what happened by inserting the zeros? By inserting the zeros in frequency domain, I got this problem. And how to overcome this problem? Just insert a filter, okay, which will have a passband characteristics from minus pi by I to plus pi by I. Okay. Now, this is all about interpolation problem. Let us go to decimation. And let's see what happens if I do decimation. Again, in decimation, I have an input. I decimate by a factor of d. Okay. So I have here fx and I have here fy, which is nothing but d times of fx. Sorry, it is not d times of fx, it is fx by d. It is fx by d, right? So that is downsampled. Okay, applying the same concept, this I can write as omega x, which is nothing but 2 pi f by fx. Omega y, if I wanted to find, that is nothing but 2 pi f upon fy, where capital F is the analog frequencies. Okay, and if I impart the relation of fy as fx by d, then what it will be? Omega y will be equal to 2 pi f by fx by d, okay, which I can write it as, this d will come up, so it will be d into 2 pi f by fx, but 2 pi f by fx is omega x, so I can write as omega y equals to omega x times of d, or d times of omega x. Very important observation. That means my frequency domain characteristics is going to get expanded by a factor of d. Okay, let us analyze with the same example. We again take the same z domain characteristics, where I have x axis as omega, y axis as x of omega with x, and the characteristics is from minus pi to plus pi, okay, and at 0, and then this will be the copy at 2 pi and minus 2 pi. The same thing is going to happen. So there will be a copy of the sequence, because the sequences are periodic in nature, and so on and so forth. I am not drawn to be very particular in scale. I am very much concerned about what is happening in this region, because these are any which ways the periodic versions of the same information. Okay, I am very much concerned about what is happening in this area. Now I am downsampling it, so I am going to get a new version of x, and that new version of x across omega is x of, I say, omega y, and we know that omega y is now equals to d times of omega x. Correct? Now what is going to happen? If I put at omega is equal to 0, okay, omega y will also be 0. If I put d equals to, let's say, if I put, no, not d, yeah, we have to consider some d. Let's say d equals to 2, because then it will be very much a generalized case. If I have d is equal to 2, then omega equals to pi, okay, will be what? Omega equals to pi will be, omega x equals to pi. If I put omega y will be equal to 2 pi. So now whatever was happening at pi will now happen at 2 pi. So now let's say this is my pi, this is my minus pi, this is my 2 pi, my minus 2 pi. Okay, whatever was happening at pi now will go up to 2 pi. So there was a trail till pi now first, now it is trailing till 2 pi. Here also it will trail till minus 2 pi, because if we consider minus pi over here, it will be minus 2 pi. So previously it was this much area, now the area increased. What has happened? Decreasing the sampling rate, increased or spreaded, or we can say expanded the frequency domain characteristics. Now we know that there was a signal, or there was some value at 2 pi also. If there was some value at 2 pi, if I impart 2 pi over here, okay, it will give me 4 pi. So whatever was happening at 4 pi will now happen at 2 pi. And if you consider at 4 pi, there will be a same replica. So what is going to happen? There will be an image coming from this side due to spreading of this characteristics, and there will be image from this side due to spreading of this characteristics, and there will be some problem in this region. Can you see? There are spreading of, this is also spreaded. So but obviously these guys are also going to get spreaded. So when they will spread over this region, and he will spread over to them. So what is going to happen? There will be overlaps, or we can say there is a folding. This is called as frequency folding. And due to this frequency folding or overlap, there is a problem occurred, okay, which will restrict us, or which will not give us a proper reconstruction of the original signal, and that problem is called as aliasing. So due to overlapping of, or due to spreading of the spectrum, there is an overlapping, and due to overlapping there is a problem called aliasing, and we cannot reconstruct the signal properly. So what could be the solution over this? We know that the signal was spreaded by a factor of d, correct? So why not to restrict our input signal by a factor of d? Okay, instead of sending omega x, if I say omega x by d, if I send that signal and multiply by d, then I am going to get omega x back, right? So what we normally do is, we normally impart, now I will just draw it with another color so that you can understand. I will impart a filter Okay, the green curve, can you see the green curve? Yeah, this is the filter which will restrict my input signal. So this will restrict the signal from, okay, let's say minus omega by d to plus omega by d, or I can say that minus omega x by d to plus omega x by d, it will be having that characteristics, it will restrict, or you can say minus pi by d to plus pi by d, because here it is any which ways in terms of pi, so you can also write it as minus pi by d to plus pi by d. Okay, so now my signal is restricted or filtered first, and then sampling will occur. What this will do, once you restrict the signal up to d and then you multiply it with d again, you are going to get back this signal spreading up to pi. Okay, and these guys will also get restricted up to this point. There will not be any overlapping and there will not be any aliasing. So to avoid aliasing, along with downsampling process, we have to use filters, right? That filter will restrict the signal by a factor of d, and then we do the downsampling. So this is what the basic problem or basic observations if you see frequency domain characteristics of upsampling and downsampling process. Okay, let us summarize. To summarize, if suppose I upsample by a factor of I, and if suppose I downsample by a factor of d. Okay, if I upsample by a factor of I, what is going to happen? There will be compression of frequency domain characteristics. Okay, then the sampling rate that I am getting is omega y, or what will be the rate at which it will get compressed is depending on the factor I, which is omega y is equal to omega x by I. Then we will get images of the spectrum, and finally to remove the images we will be using a filtering process, which we call which is nothing but normally a low pass filter whose characteristics will be minus pi by d or plus minus pi by, sorry, I, not d, plus minus pi by I. Okay, and okay, similarly if I jot down the points for a downsampler with a factor of d, there will be expansion instead of compression. Then omega y is equal to d times of omega x. Then what is going to happen? Over here there will be spreading and overlapping, which will give me aliasing, and finally to avoid aliasing I will restrict my input signal by passing it through a filter, which is normally a low pass filter, okay, to avoid the overlapping. Now upsampling along with, okay, upsampling along with filtering process, that means filter and an upsampler together, that system is called as interpolator. Okay, downsampling along with the filter together, the system is known as decimator. Together the process known as decimator. decimator. Hence the factor I have used as I and D. For I stands for interpolation and D stands for decimation. Okay. So if I have an upsampler along with a filter, then I will not call it as upsampling, but I will call it as interpolation, and a downsampler along with filtering process, I called it as decimator instead of downsampler. This is what all about the frequency domain characteristics of a upsampler and a downsampler process. Thank you.